Hello and welcome to the AICE Chemistry Lecture Series. Today in this video we're going to look at Chapter 11 Section 2, which is going to focus on the reactions of group 2 elements. This section is mostly going to focus on explaining why the reactions happen the way they do, and then we'll look a little bit at a specific reaction with acids. So let's get started. So most reactions in or with group 2 elements are going to be redox reactions. They're reactions where the group 2 metals are reducing agents and they are themselves oxidized by losing 2 electrons from the to form their +1 ions. So in general, whatever the other the thing getting reduced is, what's going to happen to the metal element is that it's going to lose 2 electrons and become the metal with a 2+ charge. So, for example, if we had, let's say, strontium will go from being strontium solid to becoming strontium 2 plus 2 electrons. This is the oxidation half of the reaction. Obviously, those electrons will go to something getting reduced and will form things like strontium chloride or strontium oxide or something like that. But this is what happens to every group 2 metal whenever it reacts for the most part. It gets oxidized into the ion. Because it gets oxidized into the ion, something that's very important to look at is 2 things. Not just the first ionization energy of that metal, but also the second. Because when combined, the first and second ionization energy are going to provide the delta H for this half of the reaction. So this half of the reaction, the oxidation half of the reaction, is going to have a delta H that's going to essentially be the combination of the second and first ionization energies of that metal. So what does that mean? The smaller this enthalpy change is, the less energy it takes to do this, the easier that element is going to react. And you can see that as we go down from beryllium to barium, as we go down group 2, we have an ionization energy decrease down the group. Both the first and second ionization energies of the group 2 elements decrease down the group. And this is the key as to why they become more reactive, because if the ionization energy decreases down the group, that means that less energy is required to remove these 2 electrons from the original metal. Because notice, all ionization energies in this case are positive. So these are all endothermic processes. So the less these numbers are, the smaller the first and second ionization energy is, then the less energy this process is going to take. So as the ionization energy decreases down the group, then less energy is required to remove the electrons from the group 2 elements, and the reactivity down the group is going to increase. These elements get more reactive as we go down the group because it takes less energy to remove the electrons, because the ionization energy goes down. And now, why does the ionization energy go down? We spoke about this in 11.1. It's because of the size and shielding. As we go down, the elements get larger and the shielding gets larger, meaning that those outer electrons are less tightly held by the nucleus. This series of 3 explanations, or 5 if you want to include how shielding and size affect ionization energy, is how we explain the increase in reactivity of the group 2 elements. This is very important because oftentimes you're going to be asked to explain differences in patterns, differences in reactivity, differences in different things for the elements in the same group. This is how we explain the difference in reactivity. They are larger, meaning that they have more shielding, so the elements are, or the electrons are less tightly held, which means that the ionization energy decreases down the group, which means less energy is required to remove the electrons, which means reactivity is going to increase as less energy is needed. So this is a sequence, it's a logical sequence of how and why this happens. It's very important for you to understand this. You do not need to memorize the individual ionization energies. You don't worry about remembering these numbers, but you do need to remember the pattern that the first and second ionization energy goes down, and then the explanation as to why that happens and how that means that we have an increase in reactivity. So now that we talked about that, let's look at some specific reactions. This can be seen in the reaction of the group 2 metals with acids. Now, unlike chapter 10, where we're looking at a period, chapter 11 is going to have the same reaction for every single element in the group. For the most part, there's a few exceptions, but for the most part, whenever we have a group of elements, they're going to react identically, and usually what changes is how reactive it becomes, right? How vigorous is the reaction. And that's what we see here. Group 2 metals are going to react with acids to produce hydrogen gas and a salt. Now remember, acids are going to be anything with the general structure HX. So things like HCl, an acid, H2SO4, HNO3, HBr, HClO4. These are all acids, right? So when we react a group 2 metal with an acid, HX, where X could be chlorine, sulfate, nitrate, bromine, perchlorate, or really any anion, what's going to happen is that a single replacement reaction is going to happen. The metal is going to switch places with the hydrogen, like we learned in honors chemistry, and the hydrogen will go off by itself, creating the diatomic H2 gas, and the metal will pair up with the anion, creating MX, a salt, an ionic salt, which just means, remember, salt means compound. Salt just means compound, ionic compound. So what we're going to create is a compound between the metal and the anion from the acid. So to look at a specific example, magnesium, which is a group 2 element, M, will react with HCl, hydrochloric acid, which is an acid, to switch places and create magnesium chloride. This is Cl2 because magnesium is 2 plus and chloride is minus 1. And hydrogen gas because, again, of that single replacement reaction. Let me change the color here. Where hydrogen and magnesium switch places. Hydrogen goes off by itself, creating the diatomic ion. The diatomic element, should I say, not ion. And magnesium pairs up with chlorine, creating MgCl2 in the ionic compound. Now, this is going to happen with every single metal. Calcium, same exact thing. Barium, same exact thing. The group 2 metals don't change. This is the general reaction with hydrochloric acid. M plus HCl equals MCl2, where M is just whatever metal we chose from group 2. Cl2 again because the group 2 metals are 2 plus. And then H2 gas. So the reaction, identical in all of them. What does change is our observations. Depending on the identity of the acid, the solid may form the ionic salt that is insoluble. So we're going to see this in the next slide, but for example, if we use sulfuric acid, that sulfuric acid might actually create a salt that is solid instead of aqueous. That's why here we have MX question mark, because this might be either solid or aqueous depending on whether this ionic compound is soluble. So what is very important for you to double check from last year? Solubility rules. Now we're going to talk about very specific examples that are insoluble. So you could, for the most part, if you don't remember, assume that anything that is not the specific examples we talk about is going to be aqueous. But you should really remember your solubility rules from honors chemistry, because in order to figure out what the state of matter of this ionic compound is, you need to figure out whether it's soluble or not. Now, the other observation we're going to see is bubbles of hydrogen gas. They're always going to be produced. Because this reaction always produces hydrogen gas regardless of the acid and regardless of the group 2 element, we're always going to see bubbles. But as we talked about in the last slide, as we move down the group, the metals get more reactive. And because they get more reactive, the reaction that we're seeing here is going to become more vigorous. More vigorous when it comes to bubbles can be seen with faster bubbling. So as you can see, and you can see this in the pictures, with magnesium, the bubbling is very slow. Once we move up to calcium, to the next metal up, we have more vigorous effervescence. Remember, effervescence means bubbling. So the metal dissolve more rapidly, we get more vigorous bubbling, more vigorous effervescence, and the solution gets hot because it's an exothermic reaction. Once we move to barium, the reaction is extremely vigorous. It dissolves very quickly, the bubbles are made very fast, and the solution gets even hotter. That's because the reactivity is going to increase as the ionization energy decreases when we move down the group, making it easier for those electrons to be lost. So the reaction itself, identical for every single metal, but the observations get more drastic. We still get bubbles, we still get warmth because of the exothermic reaction, but these are more severe as we walk or go down the group. Now, this is going to happen with any metal that creates an aqueous solution. Or sorry, with any acid that creates an aqueous solution, so an aqueous ionic compound. But there is one specific example we need to discuss, which is what happens when group 2 metals react specifically with sulfuric acid. The reaction is the same. We get the metal reacting with sulfuric acid, and we get hydrogen gas and the metal sulfate in this case, because our anion here is sulfuric acid. I'm going to highlight here. The anion in sulfuric acid is a sulfate ion, so we get the metal sulfate as a product. But something very interesting happens with the metal sulfates. The metal sulfates are going to have different solubilities as we move down the group. As we move down the group, the reactions for the group 2 metals actually slow down and even stop once we get to calcium. So they start to react and then quickly stop after calcium. Why is that? Because this should be getting more reactive, right? Well, the reactions are going to create group 2 sulfates. So magnesium sulfate in the case of magnesium, calcium sulfate in the case of calcium, barium sulfate in the case of barium, and sulfates are less soluble as we move down the group. So as we go from, let me make that a normal size. As we move from beryllium sulfate to magnesium sulfate, then calcium sulfate, strontium sulfate, and then eventually to barium sulfate, what happens is that as we move down the group, solubility decreases. So these get less and less soluble moving down the group, meaning that things like magnesium and beryllium sulfates are going to be aqueous. But calcium is going to start to be aqueous, but then quickly becomes solid as we have a higher concentration. So it quickly goes from being aqueous to solid because we say this is slightly soluble. Strontium sulfate and barium sulfate are solids. They don't become very soluble at all. And so with magnesium and beryllium, the reaction just happens. With calcium, it starts to happen. The reaction starts, but then slows down because the metal gets covered in this calcium sulfate precipitate. This calcium sulfate solid covers the metal and slows down the reaction because calcium sulfate is slightly soluble. And then with strontium and barium sulfate, the reaction is extremely slow and quickly just shuts off. It just turns off. It stops reacting because the barium and strontium sulfates are solids and they're going to quickly cover that metal, not allowing it to react with the sulfuric acid. So the reaction as we move down the group is hindered by the creation of that metal sulfate that is not soluble down the group, and it quickly covers the metal and keeps it from reacting. So the reaction itself is the same. It's this right here that changes, whether that ionic salt is solid or aqueous. And as we move down the group, that it becomes less and less soluble. So it becomes more solid. It quickly covers the metal and keeps it from reacting. So again, magnesium and beryllium, sulfate, very aqueous. They dissolve. The vigorous effervescence react very quickly. Once we get to the calcium, it starts but then slows down very quickly as the coating of calcium sulfate forms, which is only slightly soluble. And then with barium and strontium sulfates, the reaction is extremely slow. The insoluble layer of the sulfate forms very quickly, and it further inhibits the reaction, stopping it altogether. So that's one thing that we need to keep in mind. It's not due to reaction. Again, and I'm going to say this again, the reaction is exactly the same as it is for the hydrochloric acid that we saw here. What changes is whether that salt, that ionic compound that's created, is aqueous or solid, where it's soluble or not. All right? That's it for section 2. I will see you all again in the next video when we discuss section 3 and the oxides of these elements.